Hello everyone and welcome back to this new section of Atos Smart Tutorials. I'm Matteo and today we'll take a closer look at the basic setting of proportional valves, specifically bias, scale and offset. These functions are part of the signal conditioning chain, which includes also linearization that we already discussed. If you are interested in linearization, please watch the related video in our channel. Direct link is available in the video description. Let's start by understanding how signal conditioning works. As the input signal for this sequence of function block, we have the reference signal given by the machine central unit or PLC through analog or fieldbus signals called setpoint. This signal passes through various conditioning sections, ultimately being translated into a value known as the demand. This signal, called demand, together with a feedback signal, will then be used as the input value to the current, spool position or pressure control PID, which subsequently determines the system dynamics and the valve's behavior. Before going deeper, it's important to distinguish between open-loop valves which operate without any transducer feedback, position or pressure. In this case, the control signal is in terms of current. For valves with onboard electronics, current bias values are factory calibrated. For valves without onboard electronics, factory current values are indicated on a label attached to the solenoid after testing. However, since this is an open-loop system, these current values can vary depending on the hydraulic condition of the application. For this reason, fine-tuning during installation on customer machine could be necessary to ensure optimal performance. Closed-loop valves, which include a feedback from a spool position or pressure transducer. In this case, the control signal is in terms of percentage of the nominal spool stroke or bar for pressure valves, allowing more precise control and automatic compensation for system variations. Now, let's analyze more in detail each parameter. We'll start with bias and scale function for direction and flow valves with positive overlap. In these valves, the spool is designed so that in the neutral position, the edges of the spool do not align immediately with the ports of the valve body. Instead, there is a small gap known as the mechanical overlap between the spool edges and the ports. Positive overlap has two key effects. It provides low internal leakages when the valve is in the neutral position, which is often desirable for safety and energy efficiency. However, it also introduces a delay in response when the valve begins to actuate, because the spool needs to move a certain distance before the fluid can start flowing. This inactive zone is referred to as the dead band. This discontinuity in valve's regulation, caused by the dead band, can be corrected using the bias function, also known as dead band compensation. It adds, in fact, a fixed preset value to the set point, allowing the valve to respond immediately and deliver flow even at low set point levels. For open-loop valves, bias is an additional current given to the solenoids. For closed-loop valves, bias is applied as a percentage of the spool stroke. In both cases, bias is applied only when the set point exceeds a set threshold. Below the threshold, the demand is set to 0 A for an open-loop valve and to 0% for a closed-loop valve, while at the threshold, the demand equals the bias value, effectively bypassing the mechanical dead band. Above the threshold, the demand increases linearly with the set point. The default threshold is typically 2% of the set point value, but can be adjusted anytime with our software. The threshold works as a filter, helping to prevent unwanted spool movements due to the electrical noise on the set point, when set to 0. In bi-solenoid valves, we set both positive and negative bias by two independent values. Instead, scale function limits the maximum solenoid current or the valve spool position, controlling how far the spool can move at the full set point. This is useful if you want to limit the actuator speed or you are using an oversized valve and you want to reduce the maximum flow rate. Also for the scale, for bi-solenoid valves, you have to set two different values for positive and negative regulation. Let's take a quick look at how to adjust these functions on our ESW software. Under the regulation block, you will find both bias and scale settings. We pass now to a practical example. In order to set the bias, you have to adjust the set point slightly above the threshold. After that, you have to increase the bias until the actuator starts to move. On the other hand, if you want to set the scale, you have to adjust the set point to ±100%. After that, you have to adjust the scale to limit the maximum movement. As you can see, in fact, the demand decreases as well. Let's see now the effect of bias compensation on our hydraulic motor. In fact, you can see that before bias activation, the motor starts to move with a certain delay, while after bias activation there is a smooth movement of the motor. Now, let's have a look at directional valve with zero spool overlap. In this case, there is no mechanical deadband, because the spool edges align precisely with the ports. This means that oil starts flowing immediately as the spool begins to move, and therefore deadband compensation function is not necessary for this category of proportional valves. These valves are factory calibrated so that, in the neutral position, the pressures at A port and B port are equal. However, if the connected cylinder has differential areas, that is the most common scenario in industrial application, equal pressure will result in unequal forces. These forces imbalance cause the cylinder to drift even though the valve is in its neutral position. To avoid this effect, an offset must be introduced which acts on pressure gain. The offset shifts the spool slightly even when the set point is at 0%, to a position where the pressures create equal and opposite forces on both sides of the cylinder. This ensures that the actuator remains stationary when the set point is 0%. To calibrate the offset with the set point at 0%, you have to adjust the offset value until the actuator stops drifting. This fine-tuning aligns the hydraulic forces compensating for the cylinder asymmetry. Scale function here works as the same way we just saw for positive overlap valves. Until now, we have analyzed directional and flow proportional valves with positive and zero spool overlap. Now we'll talk about pressure valves, and in particular for pressure valves, bias corresponds to the minimum regulated pressure. The procedure for open-loop pressure valves is the following. For relief valves, set the set point slightly above the threshold, for example at 2.1%, and then increase the bias until the pressure starts to rise. For reducing valves instead, set the set point slightly above the threshold, and then set the bias to reach your desired minimum pressure. The procedure for closed-loop valves is the same without considering the threshold, which is not necessary for valves with integrated pressure transducer. Scale for pressure valves limits the maximum pressure. For instance, if your relief valve is rated up to 100 bar, but you only need to work up to 90 bar, you can adjust the scale so that 100% of your set point will correspond to 90 bar instead of 100 bar. This gives you better control resolution in your working range. We have discovered how bias, scale and offset help fine-tune proportional valves for system better accuracy and smoother motion control. All these functionalities are available from our PC softwares or Atos Connect app for smartphones and tablets. Thanks for watching and see you in the next Atos Smart Tutorials.